Hello friends, welcome to this session of Learning R, and today we are going to explore principal component analysis or PCA and why it's crucial when dealing with datasets that have many features. When we have multiple features like in our resin dataset where 7 features are there, it is easy to get overwhelmed in terms of complexity of that dataset and in terms of computation required to process that dataset. Models will take much time to get fitted. Features might overlap or repeat the same information, which makes the data hard to interpret. And PCA helps simplify this by reducing the dimensions of the data, keeping only the most important information or the most important variations as combinations of those original variables into principal components. We are going to understand that as soon. This is especially useful when we want to visualize data or reduce computational complexity, and PCA is most of the time used to make the model simple, to fit easily, to fit with less computations required, to take less time in fitting. Let's look at our resin dataset with 7 key features, and those features are area of the resin. The area measures the size of the resin. Major axis tells us how elongated the resin is, while minor axis length tells us how wide it is. Eccentricity measures how stretched out or circular the resin is. And then convex area shows the area of the smallest convex shape that can enclose the resin. And extent measures how compact the resin is within its bounding box. And then a perimeter is the total boundary length of the resin, indicating surface irregularities. And why we are going to use PCA. These features are often related. For example, area and convex area are closely linked because both describe size, and major axis length correlates with eccentricity. This overlap is where PCA becomes useful. PCA takes these correlated features and combines them into new principal components which capture most of the variation in the data. This helps us reduce the data set to just 2 or 3 components, making it easier to understand and visualize. By the end of this video, you will learn how PCA can transform this data set into meaningful components, making it much simpler while keeping the most important details. And at the end, we are going to fit a classification model using the principal components and how efficiently it gets fitted. We'll try to compare the model fitted using the original data and model fitted using the PCA also. Let's go to R Studio and let's start coding for PCA. Let's load the libraries first. Library read Excel, that is required to read the Excel data into R. Then library tidyverse, that is required because it's a bundle of packages like ggplot2, tidyr, dplyr. All those packages are required for function ggplot, select, filter, mutate, which are required to understand the data, mutate the data, and reshape the data. Then ggfortify, this function actually provides us visualizations for these statistical results like autoplot for visualization of PCA and other models. Then caret package is there, which are going to use at the end of this video to fit models, and that caret package provide functions to fit models efficiently. Then facto extra is the package which we are going to use for extracting and visualizing PCA and clustering results. fviz PCA index and fviz PCA variance we are going to use there. Then library ggextra, that adds marginal plots to ggplot2, functions like ggmarginal. We are going to visualize the marginal histograms or marginal density plots to see distributions of our data, original data on the principal component analysis. Then library corplot is there. We are going to see correlations between the features of the dataset, resin dataset which we are going to use here, and we will understand how those features are correlated with each other, and redundant features, how those can be combined in PCA principal components. Then grid extra, we are going to use that grid extra package. We are going to use that, we can use the patchwork package also to arrange multiple plots together to get a coherent view of all those visualizations which we have created. Now let's load the data. Here we are setting the working directory to erworks PCA, because in this directory I will go to that PCA. In this directory we are going to save the data, and this resin data set is there. This resin data set we are going to import here using the read excel function. Resin data read excel, we can use read xlsx function also, because we know the extension of the data read xlsx, and when we run that, resin data set will be in our directory, and the structure of resin data will see that it contains 8 variables and 900 observations are there. Area, as we have discussed earlier, major axis length, minor axis length, and all those. This class is the character variable, and we need to convert this class to factor variable for using in principal component analysis. Then we'll see the distributions of that by using this for loop. Features I have selected using this. These features are there. The 7 features are there. We are not going to use that class for this purpose, because we can't plot density plots for class, and I will run this and we'll see densities of those here. This is a density of the parameter. This is density plot for extent. We can see that this is skewed towards the x-axis, towards the y-axis, and here also that skewness is there on the opposite side. And likewise we can see the skewness on this side, either left side or right side of the plot, that marginal axis length, and most of this data is unimodal data, not multimodal data. And here a little hump is there for the major axis length, and density plot area is there. We can see the core plot also, core plot and core, and for that I am going to use this again, resin data, to see correlations between those different variables, and will not customize this much. And here we can see the correlation. These dark colors are where those features are highly correlated, and we can see here that most of these features are highly correlated with each other, and very few features are there which are not that much correlated or negatively correlated. And this will help us to reduce down the number of dimensions using PCA. And it's very essential to check if our data contains NA values, and then we are going to use this is.na function in resin data. If you run that, you'll see that we'll get all the columns with true and false values. And if you make sum of this, if any missing value is there, we'll get some number, because that true will get added there in the call sums. I will run that, and you can see here that in all calls, call sums is 0, means there is no missing value in the data. We don't have to impute the data to remove out that missingness, and that's the essential step. Alternative approach is there to visualize this missing data, that is library vim is there. Here we can see the pattern in the missing data also, and we can run that, and this is where we don't have any red color. That means there is no missing data, and will not impute the missing data. And now we'll prepare the data for our purpose. Cleaning is not required, the data is already clean, but a little thing that we'll convert this categorical variable class to factor variable as dot factor class. I will run that, and we'll see the structure again. I'll here only structure resin data and resin clean, and run that. You can see that class is now a factor with 2 levels. First level is Besney and other level is K-Siemens, and we have to fit model at the end of the session to classify the resins into Besney or K-Siemens based on the features which we have selected here. Then we'll split the features and the target. Features which we will use as predictor variables, and target is the response variable. And here those features I will use select those using this select minus class, means we don't want class in those features. I will run that, and now features data is there, where we will have the features, and we'll run that. You can see the class variable is not there, and target is the variable which contain only the class here. Right. Then feature scaled. Scaling is very essential, because if you see summary of this data, and you have seen that those plots also, but we'll see the summary. Features selected, scale features only, not scaled. I'll remove that. you can see that here area is 25,000, 23,000 to 25,000. Minor axis is 9,000 to 225 only. Very large difference is there between magnitude of these variables. And area will dominate all the analysis, and will not see the variations in the smaller variables in eccentricity, that is 0 to 1. All those will get masked. Extent also 0 to 1, all those will get masked. Therefore, scaling is required, and we can do the scaling in the PCA function also, or separately also. Here we are separating that. I'll run this, and scaling will make that standard deviation 1 and mean 0. That features scaled will have to scaled, and run that. You can see that mean of all those is 0, and standard deviation will be 1 for all these, and all those are around the 3 to minus 1, 4 to minus 1. That means variations are scaled to remove those large, to make all those equal in magnitude. And now we are ready. We have prepared our data, and we are ready to fit the PCA to perform the PCA analysis or principal component analysis. And here, using this function prcomp, we'll code that again. Prcomp, there's the function associated with base R only, and feature selected we are going to use, feature scaled we are going to use for that. If you want to scale that here, you can use this scale dot argument also is equal to true. Then you don't have to use the scale features. This argument is sufficient, and when you run that, we'll get the scaling will be done first, and then principal component analysis will be done. And I'll run this, run PCA result, and again we are seeing the similar thing is has been done for area and all that. No, PCA principal components have got fitted, and now we have to interpret the results, output of principal component analysis. This standard deviation, these standard deviations are strength of those principal components in explaining the data. Here we have got 7 principal components because we have 7 variables and 900 observations. If number of observations is less than number of variables, then principal components will be equal to number of observations. But here, as number of columns is less than number of observations, principal components will be equal to number of observations only. We have got 7 observations, and the first those are sorted, actually arranged in descending order. And then first principal component is explaining this standard deviation is this much, 2.19, explain much of the variance in the data, followed by the second principal component, followed by third principal component, and here we are getting 2 less data, 2 less variance being represented by this or explained by these principal components. And rotation, these are the values by which that principal component contribute, that actual variable contributes to the principal component. And area is here, area contributes more, major axis length also contributes more, and minor axis length also contributes more to principal component 1. These other variables are also there. Then principal component 2 also, these where larger values we see are actually major contributors to that principal component. This means as eccentricity increases, PC2 will increase, and this is negative, means as extent goes down, PC2 will go down. And likewise, we can interpret all these, and these principal components which are now there, which we are going to use for further analysis. Now, basic PCA summary we are going to study. I will run that PCA summary of PCA results, and this PCA summary is there. Again here, all the data associated with that principal components has been summarized. PC1 standard deviation is 2.198, proportion of variance explained is 0.6903, and cumulative proportional is 0.693. As you go further, this principal component 1.20 to 7.9, and I think here these first three principal components explain much of the variation. Here, if you see cumulative proportion of variance being explained is 0.99 almost. That means these first three components are sufficient to explain the data almost 99%. 70% to 70% to 100% is the desired level. Here we are much above, or we are much near to 100%, therefore we'll accept that these first three principal components are explaining most of the data, while these other four principal components are not necessary to analyze the data, are less significant in analyzing the data. Then we'll see the correlation matrix to understand more core features, which we did earlier also, but this time that core plot will be much this one I will have to change that par, because I adjusted the par to show you density plots. I have not shown those density plots to you, but you can run this script and see that mf row is equal to c11 and run that, and we'll plot this core plot again to see the entire plot. And here I'll zoom that. You can see that area and those variables. Here you can see per grouping also, that convex area will also get added to these area variables. All these are highly correlated with each other, and very few variables are not that correlated. Therefore, these highly correlated variables can be combined together into principal components to get the reduced dimensional data. Now, scree plot is the plot where which principal components are significantly explaining the variations, and this scree plot we are plotting using fvig, that eigenvector one function. That PCA result will be the input first. This function is coming from facto extra. Then add labels, true labels will be added to those variables, while im is equal to 0 to 100, because 100% variation is our target. Main scree plot variance explained by principal component. This will be the title, and theme will be minimal one. And when we run that scree plot will visualize. I will run this, and this scree plot is there. First three principal components are significant here, and here the explanation of variance goes to 0.8%, means first three principal components are sufficient to explain almost 99% variation in the data, and last four principal components are almost negligible. Then biplot is the plot where those principal components are used to plot the data. First two principal components will be plotted along with the data, and the biplot will show you. And this is the biplot. This is the dimension 1 means principal component 1, and this dimension 2 means principal component 2. 70%, 20%, 20.8%, almost 91% of the data is being explained. And here, using that color index target, we have separated those Besney and K-Semen. Besney is in red color, K-Semen is in blue color. We can see that little overlap is there, but some segregation is also there. Therefore, this dimension is the most efficient dimension to show how these Besney and K-Semen are different than each other. That Elix level 0.95%, this is 0.95% confidence limit, and these are outliers there, or away from that 0.95% confidence interval. Legend title also we have given here, that class is there, and then title of the plot, that is PCA biplot with confidence ellipsis, and scale color is the set 1. You can play with this to get the biplot of your choice. Then we are going to plot variable contribution also using FV's contributors. That PCA result will be the input again. Choice to get those variables is the variables. Axis 1 and 2 axis will be used, and I will run that. Top 10 variables will be shown here, and variable contribute, and these convex area, perimeter, major axis length, minor axis length, these are most suitable one to most efficient contributors to the PC1, say major contributors to the principal component 1 and principal component 2, and eccentricity and extent are less significant contributors. Therefore, we will focus, if we are going to analyze that data further, we can focus on these 5 different variables which have maximum bearing over the outcome. Then that correlation plot, FV's PCA variance, that correlation circles will plot there, and FV's PCA, where is the function, PCA result will be there. Color variable will be according to contributing variables, and gradient columns, these are there. repel is equal to true for labeling one, and title is equal to variable correlation circles. And when we run that, I'll have to delete that because it's a ggplot object. And here we can see that major axis length, perimeter, convex area, and minor axis length, these are in one direction, and therefore these are related to each other. Eccentricity is quite away from this, and extent is quite away from this. Therefore, this will be the first principal component. Eccentricity along with the information from this will be the second one. Extent information from this can be the third principal component. Okay. That variable, that quality of representation, how these variables represent the principal components, and I will run that. And again, that we see that minor axis length till this eccentricity and extent doesn't contribute much to explanation of variance, but these are very essential ones. These are not much means are contributing, but these variables are contributing more to the variance in the data or to explain the data. Combined plots, all these plots we can combine together, this ggSave and all this. I will just remove that. It's a for loop actually, I have removed that. And combined plots, we'll see all those combined plots together, and we can zoom that. We can save that as PDF or ggSave also. That scree plot is there, variable contributions is there, PCA biplot with confidence ellipse is there, and variable correlation circle is. These are important visualizations for the principal component analysis. And this is how we perform principal component analysis to reduce dimensionality of the data. And here we have selected first three principal components which are contributing to explain most of or 99% of variance in the data. And in next session we are going to use these selected principal components for predictive modeling. Initially we will fit model on the original data, and then we will fit model on the data or model using the data reduced by principal component analysis. Now we are there in last leg of our principal component analysis, and in this session we are going to fit models using the selected principal components, and we'll compare that with the model fitted to original data. The first will fit model to the original data, and this is the syntax for that. I am going to fit generalized linear model. My response variable will be class, and all other variables, this is the formula interface where this dot signifies all those other variables in this data, resin clean data. And family I am going to use binomial because of my response data contains just two categories, that Besney and K-Siemens. I'll run that and will predict from this model using this predict function. I'll just see the summary of this model, and here keep an eye on this AIC 625, and here we have used all those 7 variables or 7 factors from this resin data. And we are going to use this predict function. Model is there, resin clean the data which we have used, and type will be response. These predictions will see, and you'll see that these predictions will be as numbers, and these numbers will convert to actual class using this syntax if else. If predictions are more than 0.5, if value is more than 0.5, we'll say that it's K-Siemens, and when it is less than that 0.5, Besney will name that. And if else predictions greater than 0.5 K-Siemens, or if not greater than 0.5 Besney, we'll run that, and we have converted those number to predicted class. And now we'll get the confusion matrix, and for that confusion matrix we are going to use confusion matrix function from caret package, and as dot factor predicted class, this one, and as dot factor resin clean class or original one, and we'll compare between predicted and original using this confusion matrix. And here we can see that accuracy is 0.8578, and 71 times Besney is getting confused for K-Siemens, and 57 times K-Siemens is getting confused for Besney. And accuracy is 0.85, quite good accuracy, 0.86 actually, it is quite good accuracy, and all other will not compare. Now we'll go to the model using PCA results, and to get the PCA results we'll have to collect those scores, and those scores will be collected in data frame as dot data frame. PCA result $x, this is actually a matrix, and this matrix we are going to convert to a you can see this matrix indices. We are going to convert that to data frame, and only first 3 columns of that matrix we are going to select as data frame. I will run this code, and in scores we can see that these 3 variables are there, and those first is the PCA1, PCA2 and PCA3. Head we should have seen, but here that PC1, PC2 and PC3. To that we'll add the class as target. We'll run that, and that these 3 variables are there, PC1, PC2, PC3, and class is there. Now this data, instead of 7, we are going to use these 3 predictor variables only, and the model will be there, model training, similar syntax. Class is determined by all other variables from the data scores, and family will be binomial. I will run that, and we'll see the model, and this model's AIC value is quite higher as compared to the K-Mean that original model value. That original model value was 625, and here that is 649. Means this model is little less efficient as compared to original model, which contains all those 7 variables. We'll see the predictions also, and we'll compare the confusion matrix. Predictions again the same one. Scores is the data. Model 1 is the model which we fitted on those principal component containing data. We'll run that. And predicted classes, again we converted those predicted classes to those categories, Bayesian and K-Mean, and then confusion matrix as dot factor predicted classes as dot vector scores class, and run that, and we'll compare the accuracy of these 2 approaches, original model containing original data and model containing only the 3 principal components. That accuracy is 0.85, and this accuracy is 0.86. Means accuracy of the model which is fitted using only 3 principal components is better as compared to the accuracy of the overall model. An overall model is little larger model, require more computation as compared to the model where we use the reduced number of dimensions, and that's the application of principal component analysis in modeling. And we'll stop in this session here, and we have seen that principal component analysis is quite useful in reducing the data, reducing the dimension without reducing on the information. And that's all for this session. If you have liked this session, please click the like button and share my video with your friends. Subscribe to my channel if you are not subscribed yet. Thanks for watching.